Hi everyone and welcome back. My name is Noor Fahmi. I'm a data scientist at #paid. And I am also steering committee member of ACE. ACE is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, visit ai.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. We currently have 14 different streams that are focused on various ML topics, and this session is in the Math and Foundation stream. Hope you enjoy it and come back. Today we have Miles Cranmer, who is a PhD candidate at Princeton University. So without further ado, start us off.
Thanks. So today I'm going to talk to you about how you can take a trained neural network model and convert it into an analytic equation that kind of represents an equivalent function to that neural network. So this is work with this list of authors. So we've collaborated a bit with people at DeepMind and then people in the New York area. So I'm Miles Cranmer. I'm a PhD student. I work in kind of a mix of astrophysics and machine learning. I'm really interested in how we can apply machine learning to accelerate astrophysics research. So I thought I'd start off by giving you some background on kind of what got me interested in this area. So I think when I was maybe third year of college, I read this interview of this physicist, Lee Smolin, and he was talking about the kind of like the theoretical physics research kind of status. And so he said this: so let's focus on quantum theory and relativity and the relation. If we succeed, it will take generations to sort out the ramifications. We are still engaged in finishing the revolution Einstein started. This is not surprisingly a long process. So when I read this, to be honest, it kind of pissed me off. I found it really frustrating that it takes so long to do physics research, and that maybe I'll be 80 years old and we'll still have these kind of great mysteries of science. So I found this really frustrating, and this is what got me interested in artificial intelligence for science. So how can we use machine learning to accelerate the fundamentals of astrophysics and physics research? So that's kind of how I got started in this. And the thing I'm going to talk to you about today is kind of, I think it's like one piece of this astrophysics research process, is kind of how do we turn data into astrophysical knowledge. So this is an overview figure of what I'll talk about today. So we do some experiments with simple particle simulations. We predict their dynamics, with what are called graph neural networks. I'll talk about those later. And then we can recover the analytic equation that was used to produce those dynamics. So this is like the spring law for these particles. After that, we apply this to this dark matter simulation. And so it's a much more complicated setup, but we can apply the exact same framework and recover these actually unknown equations that describe the dark matter, which is pretty cool. So I mentioned kind of like data to knowledge, and I guess a fundamental question here, and I don't have the answer for this. It's very complicated. So when does a machine learning model become knowledge? What's the difference between Maxwell's equations, which describe the dynamics of charged particles in a magnetic field? What's the difference between those and a machine learning model that has kind of interpolated the same data set? So one, you might say, okay, deep learning doesn't generalize. If I train it on this box of charged particles and then I apply it to some other, maybe photons, it may not generalize, but Maxwell's equations do. But another thing you can you could argue is maybe symbolic models, these simple analytic equations, maybe somehow they're special. Somehow when you reduce a model to this analytic equation, it has this special ability to generalize outside of its training set. So there's this great paper by Eugene Wigner, The Miracle of the Appropriateness of the Language of Mathematics for the Formulation of the Laws of Physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that will extend for better or for worse to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. So in this article, he kind of argues it doesn't really make sense that these simple algebraic equations work so well for describing the natural world. But yeah, it's kind of remarkable that they do. So we would like to, we haven't published this terminology, but we kind of want to start calling this a Wignerian Prior after Eugene Wigner. So it's kind of like Occam's razor applied to simple mathematical expressions. So it says that in a machine learning context, sometimes you should favor simple mathematical expressions as your learned model. So we know that this works well for mechanics, like the physics of our daily life, physics, chemistry, but maybe that doesn't work so well for like social science, biology, but we know that it works well for these other fields. And this is just some cheat sheet that I pulled off Google Images. It's just all these equations for physics, and you can see they're all kind of like simple analytic equations. And when you think about it, it's kind of weird that so much of physics is just these simple multiplication, division, constants. It's kind of weird that so much of physics is these simple analytic equations.
This is like the standard like freshman year.
Yeah, exactly. Yeah. If you study it, there's so many examples of just simple mathematical equations that describe some phenomena. And when you think about it, there's not really an explanation for why this works so well. It's kind of weird. So we call this a Wignerian Prior. So in a machine learning context, you can recover analytic expressions using what's called symbolic regression. So this is a standard technique. It's not used that much actually, but it's a way of finding an analytic equation that describes some data set. And the way you usually do it is you represent your equation as a binary tree of operators. So z equals 1s plus 3 times p minus 6. This is represented, can you see my cursor?
Yeah.
Yeah, so this is represented as this tree. And so in symbolic regression, you pick one random component of that equation and maybe you swap it with this one. And so this is kind of like how evolution works. You've random crossover, maybe you have random mutations of these operators. And this is how most symbolic regression algorithms work in discovering analytic equations.
So walk me through this for a sec. The root node, terminal node, and function node, what do they refer to?
Yeah, so we don't really need to get into the details that much, but this equation is represented by this tree. So like if you walk from the bottom up, 3 times p, and then this minus 6, and you can see that this is the same as this part of your equation. Mm-hmm. So it's just a graphical way of representing an analytic equation. And when you have it in that context, it's easier to think about kind of like picking a random node, like this operator represents this, and you kind of maybe you switch it. Instead of multiplication, now you do addition. So like 3 plus p minus 6 instead of 3 times p minus 6. So that's how symbolic regression algorithms kind of work and how you can discover analytic equations to represent some data set. So symbolic regression it's a way of recovering compact, explicit analytic equations. You can interpret them, right? I can look at this and say, okay, Z depends on SP in this with this multiplication in front of it. You can look at it and understand it well. Whereas deep learning, if you have some neural network, you really don't know what it's doing internally. It's this black box, right? And symbolic regression recovers analytic equations, and these generalize well. So, like I showed you on the physics cheat sheet, they're simple equations, but they represent a wide array of problems. They generalize really well. But symbolic regression, it's bad in high dimensional problems. So, and this is because of combinatorially, it's difficult. If you have many different variables, it's hard to find an equation to connect all of them. Whereas deep learning, we know it's efficient at learning in high dimensional spaces. So like images, we know deep learning is really efficient at learning functions on images. But symbolic equations, maybe not. So with this paper, we asked the question, can we combine both? Can we do symbolic regression, but can we do it in high dimensional spaces to kind of make symbolic regression better? So in our method, we mix these. So in our method, the deep neural network's job is still to predict the target. So it's maybe you're classifying something or predicting Y given X. So the deep neural network is still trying to predict something. But with our method, the deep neural network, you kind of break it up into small internal functions inside the neural network. And these small internal functions operate on low dimensional spaces. So the method is you design a deep learning model to predict Y given X, and X could be some high dimensional data set. And you want to have a separable internal structure that's every internal function is working on low dimensional data. So once you have that set up, you train the model end to end, just like normal. You train the neural network to predict the output. But now when training, you do what's called encouraging sparsity in the internal representations of that neural network. So if you have like some hidden layer inside your neural network, you want to encourage it to have as few variables as possible. So you try to encourage sparsity. Once that's done, you have this neural network with all these internal functions that operate on low dimensional data. And then what we do is you fit symbolic expressions to each distinct internal function inside the neural network. Then after, you have symbolic expressions that represent each internal function, and you compose these together.
Interesting.
And so you do that, and since symbolic regression, now you're just operating on low dimensional spaces. So it's a lot easier to do with symbolic regression. And then you just compose those together, and now you have a symbolic kind of approximation of your neural network, and it's operating on a high dimensional space. So we do this on graph networks. So a graph network operates on a graph. And so in a physics context, a graph is like a system of particles, and every particle is a node in that graph. And the forces between each node is kind of like the edge in a graph. So if you think about Newtonian mechanics, you have particles, they interact with forces between each other, and then you sum these forces and you compute a net force on every particle. and you do force equals mass times acceleration, just Newton's law, to get the acceleration on every particle. That's this. And you use that to compute the next time step, compute the next velocity of your particles. Now, so that's Newtonian physics. And so a graph network is pretty similar. You have nodes, and these can be high dimensional vectors. So in our context, actually, the nodes are particles. You look at every single pair of nodes. So if you have like 3 nodes, that means there's 6 different pairs, because you look at each side of the pair. You concatenate those vectors. So like you have 2 nodes, so you concatenate their features. Mm-hmm. You pass that through the first neural network, which is called an edge model. And that's kind of like computing a force between 2 particles. And you compute what are called messages between these 2 nodes. So you have a message between every single pair of nodes. Then you pool these messages. So you sum them vector-wise over every receiving node. So this is kind of like you're computing the net force on every single particle from every other particle. Once you have that, you have this net message. So it's like the summed message. Then you pass it through a second neural network, which computes the updated nodes. So this second neural network is kind of like the acceleration. It's like you're computing, you have the net message, which is kind of like the net force, and then you do the equivalent of like dividing by mass to get the acceleration. Does that make sense?
Yeah, totally. I think you did a great job explaining that.
Okay, cool. Yeah, so the difference between a graph network and Newtonian physics is instead of like a 3-dimensional force vector, these messages can be 100-dimensional. And so you can be summing this 100-dimensional message and using that to compute some update. So that's the main difference. So what we want to do is turn that graph network into an analytic expression. And we do this with a range of experiments. So we have these simple n-body experiments like gravity, spring law, charged particles. And then we want to see if we take that graph network, can we recover the analytic expression that was used to generate this data set? And so this is kind of like, I think these are spring laws. So this is like all the different forces that we used. So this is our training procedure. So we have this data set of particles. And we train a graph network to predict the next step of every single particle. And while we train this graph network, if you remember those message vectors, we apply what's called L1 regularization to these message vectors, and that encourages them to be sparse. So you want to encourage the message vectors to be have only few number of variables, and then it's easier to apply symbolic regression to those messages. So if you remember in the graph network, we're kind of like these messages, we want to make them low dimensional. So they start off 100-dimensional, and we want to make them like 3-dimensional because then it's like a force vector. So this is a video of it. We start off by generating simulations of particles connected by springs. So this is what our data set looks like. We have like different time slices. We try to predict these dynamics with a graph neural network. And so I think this description's wrong. It's like the colored is the predictions. And internally, the graph network has these messages, and we try to make them sparse. So you can see the black represents how much information is in every component of those vectors. We try to make it as few as possible. So you can see that it gets more and more sparse over time. And that means it's easier for symbolic regression. So we apply L1 regularization. You can see it's less and less dimensions. So it's only 2. And if you think about it, this is a 2-dimensional simulation, right? So if there's 2 dimensions in the forces, or in the messages, it's kind of like the messages are forces. So now we try to validate it. So we see, are those messages equal to the forces? And so if it's a linear relation, that means the messages are, in fact, forces. You can see that here, they're linear. It's a linear relation between the true force and the messages. So the messages are, in fact, forces. So the graph neural network messages are actually equal to the forces when you make the messages sparse. So if we don't know this law, I mean, we kind of validated it here because we know the input force law. But if we don't know it, we can apply symbolic regression to try to extract it. Oops. Yeah. So yeah, we apply symbolic regression to the messages. And you can see that it extracts this representation, and this is actually a rotation of the true forces. So it's actually internally learning the force law. And we can rewatch this. So it learns these messages. You can see it gets less and less sparse, or more and more sparse over time. And then we apply symbolic regression to extract it. And there. Okay, so we did this over a range of experiments. We have like a spring law, and we can recover the symbolic expression for the spring law. It's actually the same one. We do this for gravity, so we can recover 1 over r squared. We can even do this for an if statement. So this is an if statement force law. So if the particles are far away, they have this force law. But if they're too close, there's no force between particles. So we can apply symbolic regression, and we actually can extract the same if statement that was used to generate those forces.
Impressive.
We also do this for Hamiltonian systems. I don't want to get into too much detail, but we can essentially recover the energy. So instead of just force laws, we can actually recover the energy too for a different, for all the same systems. So the next question we asked is, okay, so we've just validated it. We can recover known force laws that we use to generate simulations. But what we're really interested in is how can we recover equations for systems we don't know the equation. So this is like a knowledge discovery problem. So something I'm interested in is cosmology. This is the study of the universe's evolution since the Big Bang, and dark matter, which is like that's a big component of the amount of stuff in the universe. It's very important for the evolution of the universe. So what we tried to do here is, can we predict the amount of dark matter excess in a region when we take into account the amount of dark matter in a sphere around it? And there's no equation. Well, so there is an equation that was kind of like handwritten by scientists, but we want to see if we can beat that with a neural network. So the problem setting is the light parts of this counterintuitively represent the amount of dark matter. I know you look at this and think, okay, so maybe the dark parts are dark matter, but it's the opposite. So the light parts represent the amount of dark matter in this simulation. And it's what we do is we treat these blobs, these blobs like this, we treat those as nodes in a graph. And we use the neighboring blobs to try to predict how concentrated is the dark matter in the center blob. So we use a graph network to do this. And then we try to extract it using our approach of symbolic regression applied to the graph network. And we can do this. So we recover this equation, and it says that the messages you're basically, it looks like this. So the C values there are constants in the equation. And so it looks like this graph network is summing the mass of the neighboring nodes with a distance fall off. So Ri minus Rj is kind of like the distance between neighboring nodes. I think that's Ri minus Ri. That's a mistake. It should be Ri minus Rj. So it's kind of like summing the mass over the neighbors. And then it puts that into this thing, EI, and it divides by the center mass. And it turns out that that's actually an accurate predictor of the overdensity of dark matter in the simulation. And we can compare this to, so this is like the scientist form, is you sum the mass and you multiply it by the distance, by the center mass. And so we do, you sum over mass, divide by distance to neighbors, and you divide it by the center mass. And you can see that this is our loss, and we actually beat the hand-derived form by scientists. And this is also, it's not like a neural network. This is like a analytic equation that predicts that property. So it's pretty cool because we derived an analytic expression that beats the analytic expression derived by scientists. And this solution, it's accurate, it's compact, it's interpretable. Like I can actually talk about the distance falling off, right? But if you had a neural network without extracting the analytic representation, you wouldn't be able to talk about that. It would just be some black box. But by extracting the analytic expression, we can actually talk about, okay, it looks like it's actually summing mass over the neighbors and then dividing by the center mass. So that's the advantage of converting the neural network into an analytic equation, is now we can actually interpret it. And it's actually, yeah, it's more accurate than the hand-derived form. So another test we did is, at the beginning of the talk, I talked about like Wignerian priors and analytic equations being a good representation of the natural world. So we wanted to test this. So we asked the question, does this analytic equation generalize better than the neural network it was extracted from? So we repeated the same experiment and we masked, we cut out 20% of the data that had density higher than a given value. So all of the high density dark matter regions, we cut those out of the data set. We applied the exact same form, we trained a graph network, and then we extracted an analytic equation that approximated that graph network. And then we put the high density parts back into the data set. And we tested it. So we said, can the graph network predict the overdensities, like the high density regions, better than the equation? So it actually turns out the analytic equation gets 0.0892 and the graph network gets 0.142 as a loss. So that means the analytic equation generalizes much better than the same neural network it was extracted from on this data. Which is kind of like, yeah, we thought this was really cool because the analytic equation describes the same neural network, but it generalizes better. So this is kind of like a statement about simple mathematical equations generalize well to the natural world than a neural network. So I just thought I'd restate the model here. So this is how you use this approach. So you write down a neural network to train on your data set. And that neural network should have these kind of like internal functions. So that could be like a graph network where you have this separate message function and a node function, or it could be like a CNN where you have these convolutional filters and this output MLP. In our approach, you want to have a sparse latent space between those functions. And then after you train that neural network, you apply symbolic regression to each internal function. And you could use any approach for that, like Eureka, Pirate, DCGP, Deep. We use Eureka as our symbolic regression approach. And then after that's trained, you compose those symbolic expressions together. And you kind of look at this symbolic expression that we extracted is equivalent to the neural network. And so you might be asking, okay, so why don't we just do straight symbolic regression on this problem? Why do you have to have the neural network and then symbolic expression after? So let's say that our true model is, maybe it's like a time series model. So we have this time series of AI, BI, and I is like a time step. Your true model is like, it's like you're summing this function yi over your time series, and that expression is exponent of AI squared plus cos of bi. And then the output is z equals y squared. So this is like the true model for your time series prediction. And say that you want to learn this with symbolic regression. With pure vanilla symbolic regression, that will take you like 10 to the 18 equations to search over. So that's intractable. That's really hard to do. But with our approach, with the neural network, what you do is you first fit yi and z. You fit those in separate neural networks. And then once you have that neural network trained, you split those and you fit symbolic regression to this neural network, symbolic regression to this internal function. And that's only 2 times 10 to the 9 possibilities. So you've cut that search space by the square root. So it's much easier to do symbolic regression on high dimensional spaces now. So that's why you want to use our approach over straight symbolic regression. Yeah, so that's the talk. So this is kind of like schematic, and we applied it to dark matter. We have code in a Colab notebook if you want to try it from this GitHub, and that's the paper.
Very, very cool. There were some listeners who had questions today, so I'll field those. So the first one is from RSWT, and he's asking, do you have a set number of small functions, or is it learned by the model? I'm talking in context of the small functions from the neural network.
Good question. So with all of our approaches here, we just have 2 internal functions. We have an edge model and a node model. And then the Hamiltonian version, we have a global model. So it's like 1 internal function, but it actually doesn't matter. So you can apply this to any neural network as long as you have some internal functions. So all you have to do is at every latent layer, you encourage sparsity. So any neural network, as long as it has some internal functions, you encourage sparsity at every internal layer, and then you just fit symbolic expressions to each internal function and you compose them. But that's, we only demonstrated it for graph neural networks out of simplicity, but it's really, that should work for any type of model.
Awesome. Let us know if that answers your question, RSWT. The next question is from Xiang, and he's asking, could you comment on the amount of data required to perform the regression successfully?
So to train the graph network, I mean, I guess it really depends on like how complex the neural network is. I think for us, the dark matter example, we had 200,000 different examples, but I don't know generally. Now, if you're asking about symbolic regression, we only used 5,000 examples of the neural networks. So like we train the neural network, then we separate it into the internal functions, and then we use those as like a data generator. So we record the output of that neural network 5,000 different times, and then we use those 5,000 examples to do symbolic regression. So you don't need that many examples.
Awesome. And then one last question from Iggy. He's wondering, human-generated symbolic functions are built on physics foundations or a mathematical model inferred from the data observed. If it's the second, it makes sense that ML provides an optimized equation.
So I guess he's talking about this. So what's the question again?
It was more of a comment than a question the way it was phrased, but I'll read it over. He said yes, in terms of what he's referencing. So human-generated symbolic functions are built on physics foundations or the mathematical model of the data observed.
Yeah, so the scientists like to write this expression down. It relies on physics foundations. So the overdensity is kind of a statement about the density. So you would think that, okay, if we're talking about densities, we should sum over all the neighbors, because that's kind of like the density in a ball. But what we found kind of counterintuitively is that you should also sum this expression here, another constant, and you should also have a distance fall off. So we thought about this a bit, and it seems like that statement there about C4 existing, this could also be built upon physics foundations. If you think about the matter that's not included in the dark matter simulation. So maybe C4 here is like gas. So maybe it's things that were not included when you thought about this as a scientist. So this kind of makes sense, but it's just it wasn't included in the handwritten model.
Awesome. So I think that's all the questions from the audience today. I want to thank you, Miles, one more time for coming in and presenting for us, and thank the audience for joining us today. Oh, sorry, do you want to say something?
Oh, yeah, just thanks for having me again.
Oh, totally. Thank you for coming again. And one more time, guys, if you'd like to see more free content like this, visit ai.science and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish.